Hello, and welcome to this RFMW and Marki Microwave webinar. My name is Katie, and I will be your Global Spec moderator. Now I'd like to officially introduce today's presenter. Today we have Harley Berman. Harley is the Product Marketing Manager with Marki Microwave. Welcome to today's event, Harley. And with that, I'd like to pass things along to you to get us started. Go right ahead.
Great. Thanks, Katie. And thanks, everybody, for attending today's webinar. Today, we're going to be discussing a very important component that exists in nearly all RF and microwave systems, which is the power splitter or power combiner. The goal of today's talk is going to be to build up power dividers from the ground up. So what are they? What specs are important and why are they important? And then most importantly, how do you actually design a high performance or broadband power splitter power combiner? So without further ado, let's begin with our shared goal that everybody on this call, I believe, can relate to, which is that we're all in the business of detecting and demodulating or modulating and transmitting information as radio waves. In the most abstract terms, this shared goal is accomplished with a high-performance transceiver. So it's shown here. Now, these transceivers exist in a highly congested domain where there's signals in air, land, space, even cyber signals. And these modern transceiver systems have to operate in this complex environment where there's all these different things overlapping in frequency spectrum. This complex environment demands adaptive and high-performance RF systems that are capable of managing and detecting and responding to a wide range of signals in real time. So what typically exists inside of this transceiver that allows it to achieve all of these goals? Well, most or many modern radar systems, we're going to be dealing with a phased array. Now, these are unique because they allow you to steer a beam electronically without actually physically moving an antenna. And this is a big upgrade from older systems that actually mechanically rotated to scan different areas. Now, here's the high level of how something like this works. Instead of one large antenna, a phased array uses an array of many smaller antennas, and then uses things called beam-forming ICs, which can adjust the phase of the waves that each antenna sends out, well, the phase and the magnitude of it. And that allows the system to steer a beam with directionality by adding signals in phase in certain directions and canceling them out of phase in other directions. And you can now scan this complex environment much faster and track multiple things with less interference. Now, this talk is not going to be on phased array design. It's going to be on this critical component that exists within the phased array right here, which is the power divider. Now, the goal of the power divider in a phased array is to evenly split the signals across all antennas. And it's this uniform distribution that is key to performing a precise and steerable beam, which is what enables the radar to track multiple targets, etc. So let's take an example of one of these receivers where a typical receiver array could have 64 elements or 64 antennas per side to create the array. So in the corner here is a subsection of that array. However, the real phased array is going to copy this subsection 8 times over to create the 64 elements per side. So that is a total of 4,096 antennas, which is a huge number of antennas that need to receive signal from the power divider. So in this example system, how many total splitter combiners are needed? Well, the subsection shown here has 64 antennas and uses 5 splitter/combiners. So let's just see what the array, the full array, would look like if we package all of this up into this smaller blue square. And here we see each blue square contains the 64 antennas 5 splitters, and 16 beamforming ICs. And each of these need power dividers to interface between them. So we're showing 4-way dividers or combiners. And it comes out to a total of 341 total splitter combiners for the system. Now that is a lot of parts. So what exactly are these and what makes them special? I mean, what stops me from just splitting my transmission line in 2 and calling it a day? Well, the short answer is, I mean, technically you can do just that. You can split the transmission line. It will divide the input signal into 2 equal copies with identical phase. However, doing this highly simplistic approach comes with some undesirable side effects. First, you're going to run into reflections and impedance mismatches. So while the voltage on each branch of this divider here will remain equal, the current needs to split between the 2 of them, and this can't happen instantaneously for a wave. So no matter what in this design, you will get reflections. You can mitigate the reflections by making these output lines half as wide, but now we have a new issue, which is that these output lines have a different impedance than the input, again, disrupting signal integrity. And then the other major concern, if you were to just simply split your transmission line, is you have inherent crosstalk between the outputs. Now, in a power divider, this crosstalk is typically referred to as isolation. And the isolation with this approach is going to be minimal, meaning the port here and the port here can interfere with each other, and they can talk to each other. Now, it might not be a problem if the outputs have the exact same load, but any difference in output loads, and you will see degraded signal quality as the signal moves through the power divider. So what should you do instead? Well, there's many approaches to splitting power with various different power splits, various different phase relationships between input and output and the multiple outputs. However, today, we are going to be doing a deep dive into just these top 2 approaches shown here, as these are the most common for in-phase equal power splitting scenarios. So these are the resistive power dividers or power combiners, and the Wilkinson power splitter power combiners. And we're going to explore these 2 architectures through the lens of this design example here, which is we're tasked with designing an 8 to 12 gigahertz 4-way splitter for this phased array radar. This radar has an isolation spec of 15 dB for the power divider, which is realistic and achievable. The package size for components like this in a phased array system is heavily influenced by the frequency of operation. Typically, antenna elements are spaced about a half a wavelength apart at the highest frequency of operation. So this determines how small components between those elements need to be. So for example, using this, at 12 gigahertz, the spacing between antenna elements is roughly 12 millimeters, meaning the splitter combiners need to be a fraction of that space, leaving room for beamforming ICs and other essential components. So as a result, we are going to need to design an extremely miniaturized, high-performance power divider, power combiner, which can be packaged into a 3x3 millimeter or smaller surface mount package. All right, so we've set the stage with our design example, but before we actually go into how do we design these power dividers, it's important that we all are on the same page as to what exactly defines a high-performance splitter or a high-performance combiner, as in which key specifications do we need to pay attention to, and importantly, how do these specs impact the overall system that we're designing for? So let's very quickly discuss what really matters when designing a high-performance splitter slash combiner, and then we'll go into the actual design techniques. Beginning with, what exactly is this thing? What is the goal of the power divider? Well, at a high level, it is to split and combine the signals, but specifically to split and combine signals in a specific and predictable manner. And this naturally introduces the first and most obvious metric of a power divider, which is insertion loss. So insertion loss in a power divider or combiner, insertion loss is the loss as the signal passes through. In this splitter scenario we're showing here, the minimum theoretic loss is going to be 3 dB at minimum because we're always splitting the signal in two. So you're losing half the power just like that by going from input to any one output. On top of this, there is always some excess insertion loss. This is due to device imperfections or parasitic resistance somewhere in the circuit. And in the phased array system we're designing for, where we have hundreds of these power splitter combiners, this poor insertion loss will accumulate and severely impact the signal quality, reducing strength and thus the distance at which we can actually scan. Now, the quality and predictability of that power split is defined by its balance. Here, I'm showing amplitude balance, which is defined as the relative difference in output levels for a given power split. So in an ideal power splitting scenario, we will have 0 dB amplitude balance, ensuring that the power coming out of each port is identical. In a phased array system, this is incredibly important since an imbalance in the splitter will lead to an uneven signal distribution, which will affect the directionality of your beam because your antennas are not receiving the exact power that they expect to receive. Much like amplitude balance, the other side of this is the phase balance. And the phase balance refers to the relative phase between the two outputs. In an ideal dividing scenario, the output phases should be perfectly aligned, so 0 degrees apart. And this ensures that the signals, when they leave the divider, arrive at their desired location at precisely the same time. So in a phased array, this is critical for proper beam forming and signal coherence, because uncontrolled phase balance out of the splitter or combiner puts more pressure on the beam forming ICs and can lead to signal distortion, which affects the accuracy and the effectiveness of the entire array. And lastly, we come to isolation. Now, isolation measures how effectively a power divider can prevent signal leakage between these two output ports. And nearly all applications, not all, but nearly all applications want high isolation, particularly phased array systems. Because in a phased array, the isolation here describes the power divider's ability to absorb out of phase signals. So if we take, for example, a perfectly in phase signal at the two ports on the right, the instantaneous voltage across that resistor is 0. So no current flows and all the signals combined to the output. Now, as you move these signals out of phase, that resistor begins to eat up some of the signal, rejecting off-angle signals. And this directly impacts the directionality of your beam, especially in a receiver scenario. All right, so that wasn't too bad. Those are the specs. That's pretty much what we care about when designing, thinking about, and looking at power dividers. Nothing too complicated. A passive device with an S3P file will characterize the entire thing, but particularly understanding how the specs impact our design goal. So, with this understanding of the specs, let's actually dive into our first real design. We will start with the basics, which is a simple resistive splitter or combiner. A resistive divider uses resistors for splitting and for isolation. They are by far the simplest and easiest design to understand and implement. they can be made very, very small and even handle a very wide range of frequencies, all the way down to DC to probably tens of gigahertz, depending on your assembly and layout techniques. However, they do come with some significant drawbacks. Primarily, as we're going to see, high loss and poor isolation, as well as the physical layout challenges. The high loss itself is just inherent to the resistive topology, because on top of the 3 dB loss that you get from simply splitting power, there is real ohmic loss in these resistors. Additionally, isolation is only provided through resistors, so typically for low splits, it's equal to the insertion loss itself. Sometimes you'll achieve better isolation, sometimes you'll achieve slightly worse, depending on which paths you're looking at, but it's typically around the same as your insertion loss. You can sort of see that in these circuits here, because this is pretty much what the physical layout looks like. If you look at the isolation from port 1 to 2 here, that path is a less lossy path than, say, looking at the isolation all the way to port N. So you'll have better isolation from non-adjacent ports, but you're still limited by the isolation of adjacent ports. Likewise here, we see the insertion loss from any one input to output is the exact same path as any output to output. So this is a case where your insertion loss and your isolation are equal. These two are cases where they can be equal, they can be a little bit better, a little bit less, but you're never going to get great broadband isolation across all ports. For all these topologies, though, the direct, the delta, and the Y, the resistors themselves, the physical component choice, must be chosen very carefully. We commonly will see 0201 size for the high frequency use, but also the assembly itself, which we'll go into, needs to be very careful to avoid any resonance on board. Now, the direct topology on the left is the simplest design. It's easy to understand and implement. However, it does come with some trade-offs. And one of the major issues that this design has compared with the Y and the delta is that all the power dissipation occurs across fewer resistors. So what this means is each resistor in the direct topology has to handle more power. This limits the total power capacity of the entire splitter circuit. Now, additionally, in the direct topology, the layout can be quite challenging. The layout of the direct topology closely mimics the circuit we're showing here. So you could see how this can get quite tough to lay out, especially for high order splits, versus these delta and the Ys where they're kind of fanned out a little bit more. Now, these Y and delta topologies have their own set of challenges. First, one of the big challenges of this is they can only achieve power splits in powers of 2, like 2, 4-way, 8-way, 16-way. And you can see that just based on how the topology is laid out here. Now, second is a problem with all of these is they come with a nominal insertion loss of 6 dB per split. So for an example, an 8-way splitter results in 18 dB of loss. Now, this is similar to the losses found in direct topologies. However, as we showed, these two here, the delta and the Y, you can get higher isolation on non-adjacent ports. But we're going to see a design example of the direct and either the Y or delta. Electrically, the Y and delta are equivalent circuits. So how do we design these? How do we select the resistors? And how do we turn this circuit diagram into a power divider? Well, it's all about just maintaining impedance matching at each ports to minimize loss and reflections. Each topology can be worked out with your EE101 circuit analysis, and you'll get these resistor values. So let's take a look at a real resistive power divider and see how this topology performs. For this, we're going to look at the Marki Microwave, the PD0030 SMG. This is a 2-way surface mount DC to 30 gigahertz resistive power divider. And as would be expected, the insertion loss is fairly flat and 6 dB across band. So 3 dB from the power split, 3 dB an ohmic loss. The isolation in this design would be equivalent to the insertion loss in the top left, because again, I'll go back a slide just to show. It's going to be this direct or the Y topology. They're identical for a two-way. The path it takes from input to any one output is the same as any one output to each other. So the isolation is the same as the insertion loss here. Return losses are better than 15 dB across band, indicating a good broadband match, and the amplitude and phase balance are quite flat. Now, those three plots, this is due to both the careful selection of resistors, both value and physical size, but also the layout and assembly techniques. So we owe this performance primarily to our strength in 3D modeling of the transmission lines and the package parasitics. Because yes, even for a simple resistive divider, a full 3D model is going to be needed to achieve high performance at 30 gigahertz. So let's use what we've learned to try and design the power divider for this system. Again, our objective is here, an 8 to 12 gigahertz four-way splitter with 15 dB channel-to-channel isolation in a small, less than 3 by 3 millimeter package. Now, some of you may already see the problem we're going to run into, but we're going to go ahead and move forward with our design. If it were me, I would start off with the simplest of designs, which is the direct topology. All resistors are the same value. Running the equations that we showed earlier, we get a circuit that looks like this, and the simulated performance on the left. And this is exactly as expected. We get a 12 dB loss because the ohmic loss plus the four-way split now. And what we're plotting here is insertion loss from input to output on all inputs to outputs, as well as one adjacent channel isolation and one far channel isolation. And it's very easy to see, no matter what path we're taking on this power divider, electrically, it's identical. It's going through two resistors. So while we're getting good broadband performance, our isolation and our loss are all equivalent. So great job meeting the 8 to 12 gigahertz four-way split. However, this won't meet our 15 dB channel-to-channel isolation because the paths are all identical. And it never will meet that isolation spec. So we have to try a new topology. Up next, we could simulate the direct Y topology. Now this is the topology we probably should have started on. This is a much easier topology to lay out physically on the board. It's going to be less crowded. And we get a higher power handling because now we have significantly more resistors to split all the power through. Let's take a look at what we get for simulated performance again. Again, we're showing all the same paths. So we're showing input to each output, an adjacent channel isolation, and then a non-adjacent channel isolation. All the input to output splits, that's this 12 dB here. The adjacent channel isolation, again, we're only going through this path here. So the adjacent channels, we're only getting 6 dB isolation, meaning we're getting less isolation than we are the isolation from input to output. The non-adjacent channels, this path, we're achieving 18 dB isolation. So that is good. That meets the spec. However, for all channels, the resistive divider topology isn't going to work for this phased array. So we meet the bandwidth, but we will never meet 15 dB channel-channel isolation across all channels in this resistive divider. We cannot meet design goals. That is not to say that this is not useful. Resistive dividers are certainly useful, but just not for this requirement. As with everything in life, there are going to be trade-offs. So there's a lot of good. This is by far the simplest and one of the smallest circuit topologies that you can implement. It's also the easiest to implement a broadband solution. We're going to do some broadband designs of Wilkinson's, and you're going to wish that we were designing resistive power dividers. very importantly, this operates down to DC, something that we will see the Wilkinson is unable to do. So if you need DC operation, a resistive divider is not a bad choice. And they do offer outstanding balance, assuming you can lay out and assemble the divider properly. Now, the less stellar aspects of this is, as we just saw, these are super lossy. In addition to the power splits, we're eating up power in the resistors, just wasting it to heat. These typically have lower isolation and lower power handling than something like a Wilkinson, because we are limited by the power handling of these resistors. Speaking of, you do need specific resistors and, again, very careful assembly to avoid resonance. Unless you're doing the direct topology, these can only split powers of 2 without introducing excess loss. You can take the Y topology here, and you can do, let's say, an even split, and then if you terminate one of these, you can get an odd number split, but now you're just adding another 6 dB of loss by having another power split. And then something I've been mentioning over and over, because I really want to make it clear, there are serious layout challenges for this direct. It is simple and easy to understand, but physically laying this out is non-trivial. So I'm going to just take 30 seconds to discuss the challenges of this resistive layout. This is pretty much what your circuit would look like if you designed it. So you have an input and a couple of outputs, or a couple of inputs and an output. First question is, what size do you make this gap? This gap here is a capacitor. You now have a capacitor in parallel with your resistor. Do you make this gap large? Do you make it small? Do you have a specific gap size in mind? What about the actual size of resistor? I was saying 0201 for high frequency performance. You could believe me. There could be an argument that perhaps a wider resistor could maintain impedance better. That's not a bad argument. So where on the line are you going to place this resistor if you're using the small 0201? How do you account for the balance of these resistors and the resistance of them? Likewise, you can't really control the fine gaps or etching too well. There's going to be some tolerance here. And physically fitting many splits. As you can see, I'm showing 3 and it's already getting quite crowded. What's the impedance of the triangle in the center? How do you handle the awful impedance mismatch in this middle section without having insane reflections? The answer is a full 3D EM simulation using HFSS or a couple days of an engineer's time. This is all just to explain that while the resistive dividers conceptually easy to understand, physically laying them out is non-trivial. Typically, as well, these are not the most expensive parts. A simple resistive divider is usually more cost-effective to just buy off the shelf than spend, the days of actually trying to design one if you want it to operate at, 30 plus gigahertz. So what kind of systems use resistive dividers? Well, if you have a system that requires DC operation, you are limited to the resistive divider. Additionally, systems that can accommodate higher loss, these are great because they're cheap. You can buy them. Affordable, I should say. They are found in systems that have low or no isolation requirements. So there are systems where the isolation from port to port doesn't matter as much as, say, DC operation or great balance. So that's another one. These do offer outstanding balance. Assuming you can design the transmission lines in and out properly, inherent to the resistive design is outstanding amplitude and outstanding phase balance. And then typically, these are found in low power systems because we're limited by the power handling of the resistors themselves. Lastly, systems that value low cost components, they will use resistive dividers because, as I said, these are often more cost-effective if you need high-frequency coverage to just buy a resistive divider than spend the engineering time of designing one and getting through all of the challenges that we laid out. Unfortunately for us, the phased array example that we have been discussing is not described by this here at all. So we can't use the resistive divider topology that we've been discussing for our phased array design example that we're designing for. That's okay. There's other topologies out there. And up next, we will be discussing the ever popular Wilkinson splitter, Wilkinson combiner. So, unlike resistive dividers, a Wilkinson divider is more like the very first one we looked at, where it uses a split transmission line. Only it uses a split transmission line and resistors for the power splitting and to provide isolation between the output ports. One of the main advantages of the Wilkinson approach over resistive is their significantly improved isolation. They are designed to minimize the interference between these channels and also utilize the transmission line for splitting instead of resistors to avoid the ohmic loss. So we still have the 3 dB splitting loss, but now we only have transmission line losses on top of that. So this makes for a significantly lower loss device than the resistive approach. However, there's going to be trade-offs. These are going to be more complex to design and implement. And they also have limitations in terms of bandwidth, because unlike the resistive dividers, these are not going to be spec'd to DC operation, from DC to gigahertz. So how are these made? Well, the theory behind a Wilkinson power divider is easy enough to follow. At a high level, you split a transmission line for optimal impedance matching. You add in this resistor, both for isolation and to match your output ports, and then you simply tune for bandwidth. So definitely easier said than done, but the fundamental ideas behind how this works is quite straightforward, and it is going to be easy to understand. So how do we select this resistor? Why do we even have this resistor? What should my transmission line length be? What should the impedance of the line be? We're going to get into all of that shortly, but first, let's start with a brief 3-port network theory review, and then we'll build the splitter up from there. Beginning with the understanding that a lossless 3-port network cannot have all ports matched simultaneously with no reflections. This is something we touched on in the introduction with the split transmission line. And I think physically, the easiest way to reason this within your head is to think of it like a stream of water. If you are to split a stream of water evenly into 2 pipes, it's impossible to do that without being any splashing back. So, in the Wilkinson, we sort of trick the circuit into thinking it is matched on all ports and minimizing reflections. And how do we do that? It's with this resistor here. The resistor introduces a controlled loss, which enables the Wilkinson divider to achieve near perfect matching by absorbing the reflected power. And it additionally provides isolation. You can see it. This is the signal path. The resistor is not in the signal path, so it's not going to waste power like in a resistive design. Only when there's a difference in voltage at this port and this port will the resistor begin to conduct and eat up that undesired signal. Because the resistor doesn't introduce any resistive loss, a ideal Wilkinson power splitter is actually 100% efficient. In reality, there's going to be some loss, but we're going to go into what that really looks like when we get into the design example. For now, we'll have to figure out, how do we select this resistor? What's the optimal resistance? Well, when the signals are split equally, the impedance seen looking into the two parallel output ports should match the input impedance for perfect matching. We want to minimize reflections. The two output ports, or the two output terminations, will add in parallel at the input, so a 2 times system impedance resistor will match the combined parallel impedance of the other two ports. This minimizes reflections, allowing it to look more like an ideal 3-port device. So what about the actual transmission line itself? We show quarter wave. That's not quite enough information. How should we design this transmission line? Again, we're going to take the exact same concept. The two output terminations add in parallel at the input. So they must be transformed to 2 times the system impedance at the output, so they combine to Z0 or Zin at the input, ensuring impedance matching at all ports. So we have Z0 looking into port 1. This is transformed to 2 Z0 at each output leg, and then the isolation resistor is there to maintain a good match at each port. So all that's left to do on this design here is to actually transform the input Z0 to 2 Z0. And fortunately, this is made very easy because we see this is a quarter wave. A quarter wave transmission line can be used as a simple impedance transformer. Brief review for anybody that forgot down here at the bottom of how to do transmission line matching. In short, you can rearrange the terms here and see that the ideal impedance of this quarter wave line is going to be square root of 2 times the system impedance. And at a high level, that is pretty much it. We've designed our transmission lines and selected our isolation resistor. There are a few tricks that you can use to optimize performance and increase bandwidth, but the core of a Wilkinson power divider is shown right here. This will offer outstanding amplitude and phase balance. That's due to the symmetry of the device, low insertion loss because there's no resistive loss, and inherent isolation. Where does the isolation come from? The other ones made sense, but where actually is the isolation coming from in a Wilkinson divider or combiner? Let's visualize what's actually happening. So imagine we have a signal applied as shown to one of these ports. It's going to enter that port with some power going to the common port, most of it going to that common port. Some will leak through the transmission line and some will leak through the resistor. Isolation comes from the fact that the signals that combine together at this port here are 180 degrees out of phase, causing them to fully cancel. Now let's look at that. The signal starts at 0 phase. This is like a phase diagram, and I'm showing reference phase. We're at 0 for the input. We go through a quarter wave transformer here, or a quarter wave section here, and that causes a 90-degree phase shift to our signal. Then a second 90-degree phase shift, and we've now achieved a full 180-degree phase shift. When these are combined at this point here, we get full phase cancellation of signals. There's another way to think of this if you don't like the phasor diagrams, which is through even mode, odd mode analysis. So here we can imagine there's 2 signals, one on each port on the right, and they're fully in phase. So the voltage across the resistor is 0. All power combines at the common port. Now imagine the opposite. Signal's completely out of phase. There's a large voltage across the resistor, and all power is eaten up through that isolation resistor. So this brings up a very key constraint to the Wilkinson design, which is bandwidth. What is the bandwidth of this device? What's the limiting factor of this Wilkinson design? The insertion loss, I mean, other than the 3 dB splitting loss, the insertion loss is just the loss of the transmission line, which is not particularly lossy. The symmetry of the device yields good broadband balance, so it's not going to be the balance that limits the bandwidth of the device. In fact, it is the isolation that limits the bandwidth of this device, because as we just saw, isolation is frequency dependent by design. When we designed the transmission line, we designed it to be a quarter wave at a given frequency. And the 180-degree phase rotation is what provides the isolation. As you move above or below the frequency that this was designed for, this null in isolation begins to creep up. And we'll actually see this in one of our simulations. The isolation begins to creep up as you leave this frequency that it was designed for. And that makes perfect sense because these transmission lines are a quarter wave at a given frequency. Fortunately, there are ways around this to achieve broadband isolation performance, and this is typically done with a multi-section design approach. So what this means is in a multi-section Wilkinson power divider, we use the same ideas, the core ideas that we just discussed. So we have quarter wave transformer sections, only now it's sectioned up as you go through the divider, where each one is creating a isolation null at different frequencies. So you have these designed for isolation at different frequencies across a given bandwidth. And then it's simply connected together. So it looks kind of like this, and then another one. And each one of these is going to be another resistor and another resistor. And of course, it's the same over there. And what this allows you to do is you now can achieve isolation across a broad frequency range by engineering these transmission lines and choosing these resistors using the tools that we just developed. This is the approach, this segmented approach is the approach we take at Marki for our very broadband Wilkinsons. So let's see what one of these looks like in real life. This is one of those multi-section Wilkinsons designs. This is the PD0220, which is a 2 to 20 gigahertz two-way Wilkinson splitter combiner that we create. So first thing we can notice is below 2 gigahertz and above 20 gigahertz, so out of band, the insertion loss is great. It doesn't really degrade, and it's certainly not limiting our performance. But it's the isolation and the return loss as well. You can see there's a spike in return loss, which kind of correlates to this dip in insertion loss, or I'll circle it here. But it's primarily the isolation here that begins to creep up, and we'll see it on this side too. So this is just showing it's the isolation that will limit your bandwidth. You're going to have decent loss. There's a bit of a phase walk off, but you'll maintain the balance out to high frequencies. But what won't happen without adding more sections and making your device physically a lot larger, because each time you add a section, you're increasing the size of it. Without doing that, you won't achieve this broadband isolation performance. The ripple here in the isolation, this is an effect of the multiple sections creating the nulls across a broad bandwidth. So this is a performance we can sort of expect out of a Wilkinson divider. We already see this is going to look a lot better for the design that we have to do for the phased array. So let's go ahead and run through this design. So for a four-way split, it's common to begin with a two-way split to ensure we meet all bandwidth and isolation requirements, and then we adapt it to an equivalent four-way split. So we'll start with a two-way split. The transmission line parameters are calculated for the center frequency, so a 10 gigahertz line and a 100 ohm isolation resistor. And that is exactly what I did here in Microwave Office. And we see, so we have the null in isolation. What we're showing here, this is insertion loss up top and isolation at the bottom. A little more than a 3 dB loss due to the split, and then whatever loss we get from the real transmission line. And we see the performance of an isolation null at the frequency that we designed for, and we slowly begin to creep up. However, this is looking good. We meet, finally, we've met our 15 dB channel isolation requirement. However, this is not a four-way splitter. Turning this into a four-way splitter is not too challenging. All we do is we can copy this two-way split and put it on the output of each split there. So this section here, this section here, and this section here are the same. We're now showing up top, this is the insertion loss from any one input, from the input here to any one output. They're all the same, and they're all about 6 dB, which makes perfect sense. Two even power splits, so 3 dB here, 3 dB here. And then isolation of the adjacent ports is exactly as simulated previously. That's this green line. And then isolation of non-adjacent ports can only get better, and that's this red line here. So this is a very promising design for our phased array system. We've met the bandwidth requirements. We even met our isolation requirements. So can we package this in a 3x3 millimeter package? Unfortunately not. Unfortunately for us, this design yields transmission line sections that are about 5.5 millimeters long each. And we need to package this in a 3x3 or smaller surface mount package. So what can we do about this? How are we going to satisfy our design requirement? What can we do to shrink the size? Well, it's actually pretty common to do this sort of accordion style design, where instead of these straight transmission lines, we curve them and bend them a little bit. And this does significantly shrink our package size quite a lot. However, we are still limited by the physical length of these transmission lines. And for this design example, we won't be able to meet our requirement. There's also some drawbacks to this accordion design. Particularly, it struggles at millimeter wave frequencies due to coupling. There's coupling here, coupling across sections here, coupling there. It just begins to eat up isolation unless it's designed for this and it's all simulated together as a full system. It's difficult to design these for millimeter wave frequencies. There's some pretty sharp bends. There's a sharp bend there. There's decently sharp bend here. And these cause ripples in your return loss and some reflections. And while it can shrink size, it's never going to be the super, super small designs that we need for this system. So there's a lot of good to Wilkinson, this style of transmission line, Wilkinson power splitter combiners. This is a phenomenal topology. Super broadband and very low loss with high isolation. That right there is key to so many applications. They are capable of millimeter wave splitting and combining, assuming they can be designed properly. A full 3D EM simulation is certainly going to be required for very high frequency use of this. Bandwidth, as we went over, you can increase the bandwidth by just adding more sections, because we're not limited by, certainly not limited by ohmic loss, and we're not really limited by the transmission line loss. It's not going to be terribly lossy. So it's the isolation that limits us. Also, you get outstanding balance through this design. And high power handling, because now we're limited by the transmission line, not the resistors. However, you do have a low end limitation. This is just due to physical size. At 500 megahertz, this becomes, I think, like 5-6 inches. So it starts to get pretty big as like a lab usage. And then the complexity in layout and simulation gets challenging, especially at higher order splits. For the same reason, the frequency is limited. The physical wavelength gets very long at low frequencies. So we can't package these with this traditional approach super, super small. And then when you do curve the transmission line, you tend to get reflections and ripple in the return loss. So it certainly does take a full 3D model or full 3D simulation and a good amount of time to get a high performance Wilkinson design. But it is the topology of choice for many, many applications, such as any application that requires high isolation, that operates at high frequencies with low loss and high power handling. This is great for them, so long as they cut off decently above 500 megahertz. So examples is the phased array. Wilkinson splitters are super popular in phased array radars. This is the divider of choice for IQ mixers, and these are super popular for just general lab usage. They have great isolation, and they can be made super broadband. Now, I recognize there's only a couple minutes left. We're nearing the end of the webinar, and I have not satisfied our design requirement. That's not leaving you with too much confidence. How do we actually satisfy all of these design requirements simultaneously? There's still some tricks up our sleeve. The way to do this is to still implement a Wilkinson design, but using synthetic transmission lines. This has been done before, where we take the transmission line. A transmission line is a poor low-pass filter, and it can be approximated by a series inductor with some shunt capacitors. That's what we're showing here. If we replace the physical transmission lines with an equivalent lumped transmission line, we can greatly reduce the footprint and the size. This transmission line at 2 gigahertz is about 1/4 inch. The equivalent LC transmission line that you can lay out and mimic is 500 micron, or 0.02 inches. So a humongous size advantage to doing this, with also some humongous trade-offs, obviously. This is a significantly more complicated design to achieve. It requires tuning of every single inductor, capacitor, and resistor. The layout is significantly more challenging, and 15 is probably pessimistic. For maybe 20 or so gigahertz designs is where this is best. What this physically looks like is taking our 4-way Wilkinson here and creating something like this. This is not actually the equivalent circuit for what we do for our LC Wilkinsons, but it gives a very good idea. In reality, the physical layout on chip is significantly more complicated, but just some general things to think about. There's always going to be stray capacitance in something like this, so typically you'll spec those a little bit lower. You might need inductors or capacitors or resistors in locations that they may not physically be on the transmission line to mimic the real device. So while a much more complicated design, performance-wise, blows doors on the Wilkinson approach that we just went over, this is a real Wilkinson power divider that we've created at Marki that uses that design trick. We can see very low loss, say 7 to 8 dB loss up to 20 gig, and that's 6 of that is just the splitting loss. So very, very low excess insertion loss. We blow our 15 dB spec out of the water with close to 30 dB isolation. And all of this is packaged in our new CSP2 package. This package, this is to scale for the dime. This is a 2.5 by 2.5 millimeter package on each side. This approach is the approach for phased array systems. For these modern systems where we have thousands of antenna elements and super, super small spacing between them, you need this incredibly high performance, very high isolation, super small power divider, power combiner. And because of this general industry need, we've been developing more and more. So this is a high level look at some of our very small power dividers that use the various topologies we talked about today. These guys on the right here are all in that 2 by 2 millimeter package, and then this is an equivalently very small package. These are enabling power splitting and power combining from 0.4 gigahertz is our lowest frequency up to 70 gigahertz for our highest frequency CSP power combiner divider. Both two-way, and this means two-way both coming in and out opposite sides like this, as well as directly out the sides of the package, as well as even packaging these four-way splitters in this super, super tiny 2.5 millimeter by 2.5 millimeter package. And it is the design techniques that we talked about today that allows us to package these Wilkinson dividers in these packages while maintaining super high isolation and low loss. So I know I went right up to the end of the time today. Really appreciate everybody for staying on and listening. I do hope you learned something. I'll get back to everybody's Q&A questions via email. We might have time for one or two in the next couple of minutes, but please feel free to send some in and I will get back to you. So thank you so much for staying, and I hope you learned something. And thanks, Katie and RFMW, for hosting this.
All right. Thank you so much, Harley. This is Katie from Global Spec again. We do have time for maybe one question if you'd like to take one. Just in the queue here, I'm just going to choose this one. Sure. Why does the CSP Wilkinson have a band pass response? Shouldn't it be a low pass response since you are creating synthetic transmission lines?
Very keen eye. Yes. So that question was talking about this plot here. All of the other Wilkinsons, I'm going to just quickly pop up. I was going to just show the other Wilkinson divider that we showed looked more like this. Goes all the way down to DC. So why does this one not go all the way down to DC? I alluded to it here in this slide. This equivalent circuit, it's equivalent to what we're looking at here, in that there's a transmission line, there's your isolation resistor. But this is not exactly what we're implementing inside of the CSP. I don't know if we're supposed to talk about exactly how it's implemented, but just by looking at this, it's very obvious that somewhere in line there is a series capacitor, which is nulling out the low frequency performance, and that just kind of goes into I guess this point here, that this is great for size reduction. You can get a super small, super high performance Wilkinson splitter, Wilkinson combiner, but the design is significantly more complicated. There's tuning, and then there are, there will be some L's and C's and R's and in places that you may not expect them to be if you're only looking at this. But so yeah, so the bandpass response is just because this is not a legitimate equivalent circuit to what's inside of this. It is just giving you the idea of how it's designed. But very keen eye and good question.
All right. Thank you so much, Harley. So we are right at the top of the hour, everyone. So we're going to wrap the webinar up right now. So Harley, I want to say a huge thank you to you for such a great presentation and for being here with us today. Thank you.
Awesome. Yeah. Thank you. Take care, everybody.
Again, thank you all for taking time to attend this webinar event. Take care, and we will speak with all of you soon.